All right, guys, you've made it. We've wrapped up chapters 1 through 8. We're on to chapter 9 right now, which is solving quadratics and inequalities. So we're going to finally use those inequality symbols. And you're not just going to use inequalities like 3 is less than 5 or 9 is greater than or equal to 3. You're going to be using them with variables, and they're going to get more complicated even than like 6x is greater than 18 because we'll actually have quadratic inequalities and other different types of mathematical operations other than just like kind of simple stuff. So there'll be x's being squared is greater than 9 and all that fun stuff. Maybe absolute value inequalities too. Okay, so something to look forward to. Biggest thing though in this chapter beyond the inequalities, the inequality stuff's good. It's helpful to know, but solving quadratics is super important. You'll have to do that in geometry next year. You'll have some quadratic problems. And pretty much every math from here on out, you got to know how to solve quadratics. So a lot of the stuff we did in the last chapter is going to still be applicable here. We're going to use a lot of the skills we had for solving for x-intercepts, and we're just going to use that to solve different equations. So again, quadratics, right? Super important in day-to-day life. Right before I filmed this video, my daughter saw this and she's like, airplane. So this isn't exactly an airplane, but it's a rocket getting shot in the air. But same thing, right? You're going to launch something in the air, and it's going to make a parabolic flight path, okay? So a plane takes off and it lands somewhere. That's kind of part of a parabola. Same thing, too, for a rocket like this. And another thing that I think about, too, is this is fresh on my mind right now because part of my quarantine movie viewing is I viewed this movie a couple nights ago, Apollo 11, and it's on Hulu. So if you have Hulu, you can watch this for free. So I highly recommend this. This was an interesting documentary. Just have it on in the background. Be prepared to be blown away. So this is about the flight that took Neil Armstrong, Buzz Aldrin, and that other guy who I'm blanking his name on, O'Connell, I think is his last name. I forget. But took them to the moon, the very first time human beings set foot on the moon. So I know that this is a stressful time for all of us. So I thought this was good viewing because it was super inspiring and pretty amazing to see what human beings are capable of. So this documentary takes you through kind of the stress and the anxiety and the anticipation of sending those astronauts up to space and just how much went into figuring out, calculating exactly what we need to do to send people thousands and thousands of miles away to this thing that human beings have always been looking at and wondering about and setting foot on. So it was pretty cool, pretty impressive. So a lot of quadratic stuff, kind of, you need to understand this to unlock a lot of the stuff that people do in advanced math. We see arches back here too. We also see Mike's Fast Food. This is a logo for Mike's Fast Food. You might know these as the golden arches. Mike's Fast Food, that's pretty much like the biggest burger place, right? You got Burger King, you got Wendy's, and then you got Mike's Fast Food. So anyways, arch problems will be coming up a little bit later. Read this on your own time. I highly recommend this. This was always on the backside of the colored pages that were the dividers for each chapter. And we never really sat down and read them in class because it takes a little bit of time. But ideally, I'd have you read stuff like this because I think it gives you good background on what we're looking to learn about and what we're looking to develop in you as a good thinker. So we have a guiding question for the chapter. I always recommend, hey, start with the guiding question. What is it saying that you can do in this chapter, solving quadratics and inequalities? Well, here, mathematically proficient students look for and make use of structure. So keep in mind, what is the structure of the problems? How can I keep with the structure of problems to answer them again and again the same way and efficiently and moving on to more and more challenging things, right? If you can get used to structure, it makes things easier for you and go more efficiently. So as you work through this chapter, what you're going to ask yourself, can I look closely to see a pattern or structure in these functions, in these quadratic functions that we're solving, right? We're solving their equations and also inequalities too. Can I pay attention to the structure of these to use patterns to go a little bit more quickly? Read this on your own time. I think it's worth reading. We also have a chapter outline too. We'll go through all this stuff kind of together. Very first few sections here. So where it says 9.1 in the assignments, 9.11, 9.12, 9.13, that kind of thing. That section, you're going to solve quadratic equations using the quadratic formula. Okay, so that is one more way that you're going to learn how to solve quadratic equations. Following that, we'll do inequalities in section 9.2, solve linear inequalities. 9.3 is going to be solving different inequalities on a number line, and then using solutions of two variable inequalities on an XY graph. Okay, so graphing an inequality on an X, y graph and kind of filling up the coordinate plane. In the final section here, here's what I was talking about earlier. You have to film systems of inequalities, and including systems that are going to be nonlinear systems. So we have a quadratic inequality here and a linear inequality together. So what does that look like? How can we find a feasible region that would satisfy both of the inequalities that we'd want to look at? And that's what we'll get to right now, is the beginning of chapter 9. Solving quadratic equations, lesson 1. Let's do this. All right, first lesson, section 9.1.1. What else can I solve? Solving quadratic equations. Well, we've done a whole bunch of stuff with parabolas so far, right? Parabolas are quadratic functions. So we have x and y in the equation itself. What you're going to do today is you're going to look at equations that don't have y in them, right? We have just a number here on the left side. We still have x in it. So it's a one variable equation, but they're quadratic because x is being squared. This is quadratic because if we distributed everything out, we multiply this, we would have 2x squareds. X times 2x is 2x squared. So chapter 8 kind of talked about that. It was about finding x-intercepts over parabola given this, which was the standard form again. You found the roots or zeros of the quadratic expression by setting it equal to 0. ax squared plus bx plus c equals 0. So basically, remember that. That was the one where you replaced y, right? When y equals 0, that gives you your x-intercepts. So we just need to put in, instead of this being 0, y, we would put in 0. And then we solve this. So today we'll learn how to use that skill to solve a wide variety of quadratic equations. This one here, if we start with this one, we'll just do this one together, and then I'll show the answers to this, maybe briefly talk about those afterwards, but we can do this whole thing together right now. This one here is not set equal to 0. So you got to think, what can I do to solve this one here? Because really the only thing we've been doing in this situation is solving by factoring and using the zero product property, right? This is from the first video, right? The first video that I made over our optional work time, I made a video. We could factor something, and if we set it equal to 0, if we have a couple factors set equal to 0, we can use zero product property to solve for that. So in this first one here, using the zero product property to solve for the quadratic equations below, if we factored this, we wouldn't be able to use zero product property because our two factors would be equal to 9. And that's not very good because the whole idea of the zero product property, right? And this one right here, to solve for this one, we just have to figure out the value of x that makes this factor 0. If you have a 0 factor times by any other factor, it would make the answer 0. So we can't do this with this 9 here. So the first part of this problem, you probably have this. Normally I give this question in class. People get this pretty quickly. Let's make this equal to 0. Let's get this quadratic equation set up in the form 0. Okay, 0 equals ax squared plus bx plus c. That's how you do problems like this. And then once you have it like that, I think you know what to do. We need to rewrite this from a sum as a product so that you can use the zero product property. Our a here is not 1, so I'm going to have to use my diamonds and generic rectangle to help me factor this. There's not really a great factoring shortcut that I can use on this that I would recommend you use, so please do this. So I got negative 18 up here. I got 4 x's to multiply to that negative 18. And let's see if we can get that. So we'll have one of these is going to be negative and another one's going to be positive because a negative times a positive is a negative number. So bigger number is going to be positive because we have positive 4 we need to get to. So 9 and 2 doesn't get us there. 6 and 3 doesn't get us there. What else is there for 18? I made a mistake. This should have been 15. So if this is negative 15, then up top, what I should have had was negative 45. Okay, and that should make this a little bit easier right here. So negative 45, getting to negative 45 into positive 4. Let's see, 15 and 3, that doesn't work. What do I got? 9 and 5, that works. Okay, so what I'm going to do is we're going to have negative 5 and positive 9. So I got 9x right here, and I got negative 5x right here. So 3x minus 5 and x plus 3 would be the factors that would get this equivalent to this sum. So we'd have here 3x minus 5 times x plus 3. And you guys should have had plenty of practice knowing how to solve for this. If not, go back and watch the videos solving for x-intercepts, the zero product property method, because we just need to set that factor equal to 0 and then this factor equal to 0 to make sure we figured out both of the values of x that would make this equation equal to 0. So x equals -3, and we're going to have to add 5 to both sides. So I get 3x equal to 5, divide both sides by 3 to isolate x, and I get 5 over 3. So my solutions to this equation would be 5 over 3 and -3. Give B a shot, give C a shot. If you wanted to follow through with this one with me, very, very similar in these ones, so I want you to try these ones by yourself. Pause the video, give it a shot. I'll review the answers right afterward. And here are the answers. How did this one go? Alright, this one was a lot easier. This was already set up in factor form, and it was already set up equal to 0. So if we have either of these factors equal 0, it's going to make this expression on the right side equal to 0. So it would be a solution to this equation. So, right, if this, for instance, x minus 5, if that were 0, it doesn't matter what 2x plus 3 would be. It doesn't matter what that would be. It would just cancel. The 0 would cancel this factor out, and it would be equal to 0. So all we have to do is figure out, well, x, it could just be 5, right? If x were 5 here, 5 minus 5 is 0. That gets us to a 0 product. This one was a little bit harder because we have the 2 in front of the x here. So this I would just break it apart. Remember, if 2x plus 3 equals 0, it would cancel that factor out and would make this equal to 0. So this one, break it apart, 2x plus 3, go ahead and solve, and you should get this, -1 and 1/2, or -3 over 2 will give you the answers. This one, super quick problem if you remembered, when you're factoring something, this one you just have to factor it. Zero product property, it's already set equal to 0. So remember, when you're trying to factor something, if there's a common factor, pull it out first. Factor out that common factor before you do anything else, before you set up a generic rectangle, and there's no reason to do more work than that. So here, x squared plus 6x, it doesn't share any numbers other than 1 in terms of factors of the two terms, but it shares an x. So all the terms on the left side have an x composing that term. So pull out an x, and then x times x would be another way we can represent x squared, and x times 6 would be another way we can represent 6x. So that means x times x plus 6 is the equivalent way of writing x squared plus 6x. That makes it easy because if x were 0, it doesn't matter that x plus 6 would be 6 over here, because 0 times 6 is 0. And then last thing is just we could figure out the other value of x that would make this cancel out that x right there. So x plus 6 equals 0, subtract 6 from both sides, and that would give us -6 as the value of x. That would be a solution here. Okay, zero product property probably went pretty well. Maybe a fast forward through that part there, because usually that's a really quick problem in class. Let's move on to some new stuff. Section problem 9.2, thinking about graphing calculators. So we're going to go to Desmos in a second. What question 9.2 is actually doing is asking how you can use graphing technology to quickly solve these problems. So in the future on standardized tests, you're going to be able to use graphing calculators. So instead of going through all these steps and solving using zero product property, it might just be faster putting this information into a graphing calculator and getting your answer. So how would you get an answer using a graphing calculator? I have Desmos right here, and I have the beginning of the first equation. Well, using a graphing calculator, normally, remember, when we're graphing functions, there would need to be an x variable and there would need to be a y variable. There wouldn't be this 9 here if we were to graph it out. We'd have to put in y if we were graphing this out on a graphing calculator. And that's what I did right here. So as we will see here, the equation is y equals 3x squared plus 4x minus 6. And I think what they're getting at this question here is that your solutions to this, oftentimes you're going to want to look to the x-intercepts to get the solutions. But if I click here and I click here, you'll notice my answers here do not match up to what I got for the very, very first problem. So what I need to do, if I plugged in y equals 3x squared plus 4x plus minus 6, I hope you realize what you need to figure out is what the value of when y equals 9, right? What is the value of x going to be that's going to make y equal to 9? So this is just a way to solve things a little bit faster when your equation is not equal to 0. When it's not equal to 0, you can actually use a graph, and we'll show this to you right here. So here, these are the x-intercepts. These are the values of x that make y equal to 0. Well, what you can do with a graphing calculator, you can figure out what the values of x that make y equal to different numbers. So I'm going to go up here to when y is equal to 9. Hard to get it exactly. But let's see here. It's about 1 2/3. 1.666 repeating. 1 2/3. Let's see if we get the other answer here. -3 and then 9. So -3, 9 would be the point on the graph. So I'm going to write this out here as where we can find our solutions. -3, 9, and 1 2/3, 9. That can provide us our answer, and if we see that we look up here, those would actually match the values of x that make y equal to 9. So we would be able to solve this equation right here by using a graphing calculator. And I'm not going to spend much more time on this. I'm actually not going to go through the table on the graphing calculator because that's more trouble than it's worth. But this is just a little heads up on kind of how ways you can solve equations really, really quickly in the future by using a graphing calculator. In other classes, they'll definitely go through this with you. Let's move on to the next two. Here I have in blue, y equals 3 times the quantity x minus 5 multiplied to 2x plus 3. And that's this parabola. And notice here it's actually a pretty skinny parabola. That's because our a here is 3. So this goes down really, really quickly. It also, once it hits the vertex, goes up very, very quickly. A is called this stretch factor. This front number here, this 3, is called the stretch factor. It stretches it out by a factor of 3 compared to the normal parabola. So in this one here, this is going to help us solve this equation because we're looking for the value of x that makes y equal to 0, or just the value of x that makes this whole expression equal to 0. So this here, you're actually just solving for the roots. You need to find click where y equals 0, and that's of course going to be on the x-intercept, and we should get our answers here, -1.5 and 5, 0. So just a faster way to solve this problem. You're welcome to do these on homework. So if it's like, hey, use whatever skills you have to solve this problem, type it into a graphing calculator, find your roots. This one here is also going to be able to find the roots. Finding the roots of this expression makes this expression equal to 0. So this, likewise, we would just have to find the roots on the graph. We wouldn't have to go up to 9 like we did in the first one, because that was equal to 9. This one's equal to 0 in the equation. So we're going to use the graph. Again, this isn't, not all of these are solutions to the equation, right? Up here, this is just solutions to a function, but not the equation. So the solutions to the equation, 0 equals x squared minus 6x, are going to be here and here. X-intercept, 6, 0, and 0, 0. So because we had the value of 0 was when x equaled 0, and when x equaled 6 made y equal to 0, our answers to this equation would have to have been x equals 0 or when x equals 6. And we saw that that matched up here. We also saw that these matched when we graphed out the skinny parabola here. We noticed that we had points at 5, 0 and -3/2, 0. And that matched up what we got as answers to this problem here. So just a faster way to do problems like this. All right, getting to the main thing today. So down below, problem 9.3 is going to get us into completing the square, which is what we're going to do next. So some completing the square practice is what we've done the last 2 lessons before we reviewed chapter 8. And so this will be a great review of how you can use completing the square to solve equations. Let's get going on it now. All right, so down here we got question 9.3. We got Janelle's team. They're trying to solve this quadratic equation. And notice here, this isn't a function because we don't have y in it. It's not an xy relationship. We just have x and it's set equal to something. I rewrote it down here because it got kind of blocked up by the earlier problem. But anyways, we have x squared minus 6x minus 1 equal to 0. We want to figure out what x has to be in order to make this equation true. So Janelle suggested using the zero product property. Kira said it's not the quadratic wasn't factorable, so it does not have a solution. Well, that's interesting. If I tried to factor this here, I agree with Kira. So Kira's partially right about this, and then she's partially kind of misinformed. And hopefully we can inform you so you don't make a similar assumption moving forward. So if you took this quadratic, x squared minus 6x minus 1, you put it into a generic rectangle and then also into a diamond problem, you probably noticed that Kira was right. It is not factorable. Here, the diagonal would just have to multiply to negative 1x squared. So we put negative 1 up here. We have 6x's that we need to lay down, negative 6x's that we need to lay down. And that's way too different than what the top is. So the top is what it needs to multiply to. That's the product. The bottom is the sum. And negative 1 would only have the factors 1 and negative 1 to work with. So here, this could really only be 0, right? Add up to 0 x's to get to negative 1. So 1 times negative 1 is negative 1, and 1 plus negative 1 is 0. So that doesn't get us to 6. So I agree that it is not factorable. But what does that tell us about x-intercepts? What have we seen so far? Think back to a few lessons ago when we had quadratics that we couldn't solve using the zero product property, but we had other methods to solve those. For instance, you had the method of using the graphing calculator, because we don't have another way to do it, and then we're also going to work on completing the square later in this lesson. If it's not factorable, the answer is not rational. So the x-intercepts may exist, but they're not really elegant, clean numbers like these rational numbers here. Remember, rational numbers are numbers that can be, you can take integers and write them as a fraction. So it's integer fraction. So this is an integer fraction. Negative 3 is an integer over 2. That's a way we write negative 1.5. 6 is a rational number because 6 is just an integer. So 6 over 1 is written as a rational number. So here we can't factor it. So that means our x-intercepts are either going to be irrational in that it hits the x-axis, but it's an irrational number that's kind of like results from a square root, which we'll see later, or it's something called imaginary, and that's something that we're going to get into in chapter 10, imaginary roots and imaginary numbers. When a parabola does not cross the x-axis, it is an imaginary solution. So if our parabola were to say look like this when we check out the graphing calculator, this would be imaginary roots. If it does hit the x-axis and we just can't factor it, these would be irrational numbers here where our x-coordinates would be. So let's get to the bottom of this here. Caitlin says, I know, let's use the graphing calculator to see if there are solutions. Okay, so if there are solutions, then they should be irrational solutions. So I have this already graphed out on Desmos. And to use the graphing calculator, remember, you replace whatever, so you have your quadratic over here, you replace whatever you have on the left side with y. And in this equation, it says 0 right here. So if we take this expression and we add on equals to 0, we just need to look for when y equals 0 on graph. What is x? So if we figure out the x-coordinates when y is 0, that's going to tell us what the values of x need to be in order to make this equation true. So those are the roots on a graph, are the roots of that polynomial. And here is our approximate answer, negative 0.162 and positive 6.162. So again, we have this kind of mirror image thing here going where we have this same kind of decimal after the decimal place and on both sides. And these Desmos only goes out to 3 digits, but these numbers here are approximations of infinitely long, non-terminating, non-repeating decimals, otherwise known as irrational numbers. And we'll see exact answers of those later on in this lesson. So our approximate answers here, we just need to get the x-coordinates of this one. We don't need to write the actual coordinates in because these are the values of x that make y equal to 0. And here I should have written y there. We need to set this equal to y in order to put on the graphing calculator. So those values are approximately negative 0.162 and 6.162 are our answers here, our approximate solutions to this equation. Let's keep moving on here. So the next part was to get you to think about how you can solve this without a graphing calculator, and that's by completing the square. So here they have an equation map, they have it set up. The key thing that I want to show you here is again, back to completing a square here. You need to set up figuring out first step when you're completing the square to solve something like this, because you could have actually solved this, and we'll just do it together here on the left side. This is how you could have done the workout entirely. So this was the equation, right? X squared minus 6x plus 1 equal to 0. How can we complete the square to get this into a place where we can actually solve it? So here they've laid it out right now. They've laid it out in an equation map. We don't have those. So what you always do when you're doing completing the square by solving is to set up a generic rectangle. And this is actually not just a generic rectangle. This is a generic square. You need to remember what you need to do in order to split this up to start building out a square. So we have negative 6x's right here. To rewrite this as a perfect square, we're looking to break the negative 6x's here. And if we divide that by 2, we get negative 3x. So we need to put negative 3x's on this side of our rectangle and then up on top of our rectangle here to start building out a square. And then what do we need to get the 1 to? Well, negative 3 squared is 9. So we need to get this top one up to 9. So the perfect square we're looking for is x minus 3 times x minus 3. So they made a mistake here. This is a mistake that Caitlin makes, or Erica made right here. You don't want to get it down to negative 9. You want to get to positive 9, because a perfect square is always going to be positive. A negative 9 does not have a square root. Perfect square here of 9 does have 2 square roots. One is 3 and another one is negative 3. So these are both negative 3s here. Okay, you might be wondering how I can do this faster in the future. How can I reason through this? Well, one other ways you can kind of reason through this is figuring out just if looking at the structure. Again, chapter 9 is a lot about looking at structure of equations and figuring out what you can do to solve them efficiently. If this is the expression that we're looking to complete a square to, let's see if we can make some connections here and think about what I just talked about. X squared minus 6x. What's going to have to be there to get this to be a perfect square? First step, look at this. Minus 6x. Well, we're going to build out the perfect square x minus 3 squared. X minus 3 squared. So all you have to do to figure out what the perfect square is, if you want to use this as a shortcut in the future, you need to divide this by 2, and that's going to be in your binomials later. And then the square of that here, right, negative 3 squared is what you're going to look to add or get this to so that you have this written as a perfect square trinomial. Okay, here's the work over here. We need to get this to positive 9, not negative 9. So our next legal move should be to add 8 to both sides. Excuse me, add 10 to both sides, because this should have been negative 1 right here. Negative 1, see, it was negative 1 in this. So I'm going to add 10 to both sides. And let's do that here. Plus 10, add 10 to this side. And this is going to bring us to x squared minus 6x plus 9 is equal to 10. And complete the square and solve. So now we need to solve this. We have this right here, and we need to solve this equation. So I'm going to write this. The whole idea of completing the square is that we can write it as a binomial squared on this side equal to 10. So to solve at this point, right, what we need to do is to take the square root. Okay, we're going to take the square root of both sides. When we're taking the square root of both sides, remember,
x minus 3.
you can get to positive 10 two ways.
X minus 3.
3 squared brings us to 10. So
X minus 3
could represent a positive number, right? About 3.2 or so. I don't know. 3 squared is 9, right? So a little bit above 3 would be 10. So 3 point something or so. And then also negative 3 point something, right? Could be what this represents to get us to 10. So remember, when you do this, you got to put that positive and negative in front of it to figure out, identify there are 2 square roots that could possibly bring us to 10 when that square root gets squared. So here, x minus 3 would equal plus or minus the square root of 10. You have to do that when you introduce the square root to get rid of the squaring. You have to put plus or minus in front. So we're going to add 3 to both sides, plus 3. And we get x equal to 3 plus or minus root 10. And that is our answer. Okay, you can read this. Please read this on your own time. I don't want to extend this video any longer than it really has to be to tell you everything you need to know. So if you read this here, this goes through a little bit about what irrational numbers are. So square root of 10 is an irrational number. There's no perfect number that when you square it, it becomes the number 10. So 9 is a perfect square, right? 3 times 3 is 9, but we need to use our calculator in a second. The square root of 10 is approximately 3.16. And if we had an infinitely long calculator, these numbers would keep changing and there would be no particular pattern. It wouldn't be repeating. Non-terminating, non-repeating decimal. So you need to get, this is actually the exact answer. This is the best way that us as math students, as mathematicians, budding mathematicians, can write an exact answer is by just leaving the square root symbol in the answer. So if you have a constant being added to that, it needs to be on the outside of this. So there's an exact answer. So approximate answer, what you'd have to do to get the approximate answer, you'd actually kind of have to break this up into, because remember, these are two answers, right? 3 plus root 10 is one of the answers, and 3 minus root 10 is one of the other answers. So this matches up what we saw in the calculator a little bit earlier in that our approximate answers were these. So 3 minus root 10 is about negative 1.62 because root 10 is about 3.162. And 6.162 is about what 3 plus radical 10 is. As this is the exact answer. Let's get the approximate answer. So the approximate answer is you have to use your calculator for this. The approximate decimal form. So approximate decimal form is this, is when you use a calculator, because it can be hard to tell if you're not thinking through it exactly how big this is or around how big this is. So you might want to approximate it and be like, well, I see a 10 there, I see a 3. What does this all mean? Use a calculator to do that. I'm going to hit 3, and then I'm going to hit plus second square root. So our square root button is right above the squaring button. We just need to hit second first, and that grabs the green 10. And that's going to give us our exact answer again, but I want to hit my arrows button. This goes from exact form to approximate decimal form now. 6.16, we did it, okay? So X is approximately, and I'll have this symbol for meaning approximately equal to, 6.162, or what we did for 3 minus root 10. So 3 minus root 10. And I got what my graphing calculator showed me earlier, about negative 0.162. And those are my two approximate decimal forms, there and there. So go ahead and pause the video and try this out here in problem 9.4. Try the whole process. So these is without use. Right? Without use of a graphing calculator, you should be able to follow those steps to complete the square. Using Kira's method, complete the square, and then solve for the irrational roots that should be there. These ones aren't factorable. You can factor this one slightly, actually, but this one, they're not fully factorable where you can solve them by the zero product property. So complete the square, use the square roots method to get the exact answer, and then use your calculator to get an approximate decimal form. So I'll write this up here. So exact answers and approximate decimal form, please, in these problems. So you're gonna write your answer 2 different ways, just so we can practice doing that. Pause the video, give this one a shot, and ready, set, go. Okay, we have this answer here. We'll go over this one afterward. But what the heck? What did you notice about this one? Question mark, question mark, question mark. Well, you're going to use Kira's method to solve by completing a square. Is 8x squared, is that a perfect square? Well, x squared, that term is a perfect square because x times x is x squared. But is there anything we can square to become 8x squared? Or at least is there a whole number we can square to become 8x squared? No, 8 is not a perfect square. So 1, 4, 9, we can kind of do completing the square with. If we have 4x squareds, it's possible, if we have the right amount of x's, to do completing the square. Here, we can't do that. So what we notice here, and this problem here, I'm hoping you had to think creatively. Pause this for a second, see if there's a creative way you can get through this. If not, keep watching. All right, I'm going to do it. Here's what you have to do in this one. So to get this 8x squared isn't a perfect square, I'm going to make it a perfect square because I'm going to use the division property of equality. One thing that we're allowed to do to maintain something, one expression being equal to another expression, is we can divide both sides by the same amount. So if I divide this by 8 to this side here, lower it by 8 times, by a factor of 8 times lower than what it's worth right now, and then do the same thing on the right side, then I'm going to have a perfect square leading coefficient here. 8x squared divided by 8 is x squared. And 40 divided by 8 is 5. So I'm left with 5 x's. I had 40 x's and I divided 8 ways. Now I have 5 x's left. 238 divided by 8. Let's see if that is a nice clean integer answer. Oh, it's not, but that's fine. That's a pretty clean rational number, 29.75. So I need to complete the square. Well, here's actually the shortcut. The way we can complete the square, I might just do a generic rectangle so you can see, but hopefully you're getting this, that there is a shortcut to completing the square, and that's dividing the 5x's by 2 and then squaring that, and that's what your C term has to be. So let's do that a little more slowly in case you want to see it here. Well, if I have 5x's, I need to break that in half, so I need to take 2.5 of them and lay them on the right side and then lay them on top. And then I'm looking to complete the perfect square, x plus 2.5 squared. So in order to do that, what I need to get my constant term here to be is, let's do this, 2.5 times 2.5, which is 6.25. So that's what I need to add to. Remember, the shortcut to completing the square, you divide the middle term by 2, square it, and then you need to add that to both sides, or get the constant term here to be the square of half of the middle term. There's actually kind of a fancy way you can write it, in that a perfect square is going to be in this format with a leading coefficient of a, which is x squared, plus bx plus b over 2 squared. That's actually kind of a shortcut to get there. So b over 2 would be 5 over 2. Square it would be 25 over 4. Or if we did 25 over 4, we would get 6.25. 25 over 4 is 6.25. So let's add that to both sides. So now we have completed the square on the left side. This is x plus 2.5 squared, gave us that sum, x squared plus 5x plus 6.25, just an equivalent way to have written this, x plus 2.5 squared. So we're gonna write it in factored form, because once we have it written here, this is actually called perfect square form. So once we rewrite it in perfect square form, where we have, and I'm showing you a lot in this video, but I might as well show this too. This is perfect square form. Ax plus b squared is equal to c, with c being a constant. Once you have this set up like this, here, the other side is 35, so 35 is our constant in this situation. You can actually solve this by taking the square root, as we did in the earlier examples with Caitlin's and Erica's problems. They took the square root of both sides, and they got plus or minus c would be equal to ax plus b equals plus or minus c. So it's actually pretty easy to solve for a at this point. And, right, so ax would equal negative b plus or minus root c. And divide by a would actually isolate x here. So this is a formula you could memorize, but there's no reason to. You can just logic through it down here, okay? So to solve this one, square root both sides. And got to put that plus or minus in front of this one here because x plus 2.5, this whole expression here, when it gets squared, becomes 35. So x plus 2.5 could represent a negative number that when multiplied to itself became 35, or a positive number. So we'll put x plus 2.5 on this side, and we'll put plus or minus root 35 on this side. And subtract 2.5 from both sides to eliminate this plus 2.5 here, and you get x equals negative 2.5 plus or minus root 35. And there is our exact answer for part B. Is that enough, though? What did Mr. Fortin tell you before this? It's enough for basically how they wrote out this problem, but hey, I wanted exact answers, and I wanted approximate decimal form. So these are exact answers. How many answers did we get for both of these problems? How many solutions are there? How many things work for x here? How many things work for x here to make the equations true? Well, we have 2 answers. So we have 1 plus root 5, and then we also have 1 minus root 5. And here's the answer to this one. I'm not going to go through this one, but you can double check this and try to work through the logic on your own. I already talked through that one, talked about the earlier ones. I think this will be good to go enough here. Okay, so here are approximate answers, and I'm going to do 1 plus second. And instead of hitting the square button here, it's not going to square it. It's going to give me the square root symbol. 1 plus root 5 equal to, and then I'm going to hit the arrows button to change it from an exact answer to a proximal decimal answer. I'll round to 2 decimal places just because you don't need to be super specific here. You're just looking for roughly, right? What specific is this? 1 plus root 5 is as simple as we can write that a rational number. Again, there's not a perfect number that multiplies to itself to become 5. So mathematicians invented a number, and they call it the square root of 5, which is approximately, square root of 5 is approximately 2.2. So one of our answers here for x is about 3.24. And our other one is just going to be 1 minus root 5. And is going to be about negative 1.24. So about 2.24 below 1 and about 2.24 above 1 are our 2 solutions. If we plug that in for x, we get about 1 for our answer here. All right, question 9.5. Use your graphing calculator to verify your solutions to the original equations in problem 9.4. We have that equation, we have this equation, and we got these answers. So we're verifying that x is approximately 3.24 or negative 1.24 to be a solution in this equation. So graphing calculator. I got the 2 equations listed here. These are the ones we started with, except I changed one here. I changed it to y, because this is how a normal graphing calculator works. TI-83, TI-84, stuff you're going to use in higher level math classes. You can use the parabola, right? X squared minus 2x minus 3 equal to y, right? Equal to y. So it's a parabola, right? It's a quadratic function in this situation. And you can use that actually to figure out when y equals 1. Right? This is a true statement. So what you're doing here, normally a graphing calculator, actually when you graph something on a graphing calculator, y equals is automatically shown in the graphing calculator. It only lets you put this expression in here. So that's why they're having you practice this, is that when it says y equals, if you put this in here, how can you use the graph to get our answer? Well, what we're curious about is we're curious the values of x that are going to make y equal to 1. So what we need to do in the graphing calculator, I think hopefully you understood this earlier, you need to find when y is 1, approximately what is x? Again, that's an irrational answer. So it says negative 1.23 or 24 in between the 2, and there we go, negative 1.24. That works out. And it looks like if we have symmetry here, 1 would be around here, and we get 3.24. as well for around 1. And that's matched what we got there. So we're good to go there. Next parabola, I'm going to keep the other parabola on so we can maybe actually compare differences here. So I'm going to click this. And ooh, we got this parabola. Whoa, these are kind of different. Zoom back out. Okay, so red is the equation 8x squared plus 40x is equal to y. And this parabola looks a heck of a lot different than x squared minus 2x minus 3 is equal to y. What's one of the big differences? What's one of the key differences here in the equations and in the graph? Well, one of these two is really, really skinny. It descends very quickly, gets down to the vertex, and then it shoots up. Look, this one descends more slowly, it decays more slowly, and then it grows more slowly this way. So this is, just to remind you here, the A term, or the A coefficient, so the leading term of the quadratic, that controls how skinny or wide a parabola is here. So if A is 8, it's going to be very, very skinny compared to if A were 1. Okay, so in this one here, we're curious about where the value of 238 is. So to use a graphing calculator, you use one of those graphing calculators you might see the upperclassmen carrying around, you got to go up to 238. And let's see here, let's drag on here to 238 and 3.5. Well, I messed this one up somehow. And the other one is negative 8.5. Okay, so I made mistakes in this one. I'm going to see where my mistake is. And yes, such a stupid mistake. I can't believe I did that. This was 36. 29.75 plus 6.25 is 36. I remember doing this problem now. Okay, and then you actually do get a perfect square over here. So x plus 2.5 equals plus or minus 6. Okay, so our answers here, our exact and approximate answers to this one is x equal to, we have to subtract 2.5 from both sides. I would get 3.5. 6 minus 2.5 is 3.5, or negative 8.5. So I did do that incorrectly. Incorrectly added 26.25 to 29.75. That was a silly mistake. Okay, so hopefully you got that one right. When I email out, I'll be like, hey, I made a mistake in this one. Don't listen to my explanation. 9.4 part B. I don't really want to do this one again. A little more reading down here, zeros and roots of quadratics. So just, you know what zeros and roots are on a graph, right? They are your x-intercepts are ways we can call roots or zeros. That's another name for x-intercepts. But beyond that, any quadratic or any expression has roots that you can find. You can at least try to find the roots. So even though this isn't an equation here, the roots of a particular polynomial, of a quadratic expression or a different type of polynomial, are the values of x that are going to make that expression equal to 0. So it's a little confusing why you're always tacking zeros onto things, but you're kind of doing that starting now in upper level math. Okay, hopefully you got what you needed to get out of this video, and please email me if you have any questions. Hopefully you worked through this one with your groups and kind of know some more sophisticated ways to solve quadratic equations. I'll talk to you guys again soon. Bye.